Here's another circuit, a little bit more complicated. Now we got another bulb and the switch is around there. And again, we're answering these questions when we close the switch. Does delta VA go up, B, 2x, 0, etc. Rather than try to guess these one at a time, let's just go through all four voltages across all four bulbs, get them when they're open, get them when they're closed. Okay, same strategy as before. We start by analyzing the entire circuit by getting the equivalent resistance when it's open. The equivalent resistance is R in series with two things in parallel, or two branches in parallel. So 1 over this branch, so 1 over R plus R, plus 1 over R or D. So this is A, B, C, D to the minus 1. Now I didn't also do C, I didn't also do the switch this time. If I wanted to write in the switch, then in here I would put 1 over R plus 1 over R of the switch to the negative 1. But if we did that one mathematically before, if you have a switch in parallel, you end up realizing it's just R. Because the other resistance in parallel is infinity, so having a 1 over infinity there doesn't do anything to the equation. So I left it out this time. So if we want the equivalent resistance then, that's 1 over R plus 1 over 2R, 2 over 2R, 3 over 2R, flip it over, 2/3 R. So 2/3 R plus R is 5/3 R, is the equivalent resistance. Very nice. So the current is the EMF over 5/3 R, so it's 3/5 E over R. All right, that's the current coming out. And now delta VA. Here we go. Uh-oh, memory stick ran out. All right, let's refinish this one. So we have the current now going through the loop, and we're going to calculate, now that we have the current, we can get the delta V, the voltage drop across A. So delta V across A is just IR. I is 3/5 EMF over R, and the resistance of A is just R. Okay, so the R's cancel. So delta V over A is 3/5 of the EMF. And let's see, so next we were going to use, let's see, the loop rule to get delta V over D is the way I would go. Because you can say if I loop through here, let's see, loop or D, so if I loop across the battery, that's the plus EMF, and then I go with the current loop through A, that's minus 3/5, 3/5 of the EMF. All right, and if I decide to loop this way through D, that's minus delta VD equals 0. So you can see what you might do intuitively is the delta V, the voltage drop across D has to add up with this one to make the whole EMF. So the voltage drop delta V across D is 2/5 EMF. 2/5 E. And let's see, that leaves B and C. Well, if we loop through here, we're going to say that the delta V across both of these is also 2/5 EMF because it's sharing the same wires as this bulb. And it's two resistors in series that are identical, so they're each going to get half the voltage drop. I'm not going to do more V equals IR, but you get the idea. Then each of these must give 1/5 EMF. And this one's 1/5 EMF. All right, so 3/5, B and C are 2/5, and D is 1/5. Okay, and that was with the switch open where it does essentially nothing, right? Because it's like a resistor in parallel with C at infinity. We aren't going to write out this whole thing, including that as well. That would be hard. We could think through it real quick, unless I already said this. I forgot because it was yesterday. But if we just thought about these two, what would it be? It would be R and infinity. It would be 1 over R plus 1 over infinity to the minus 1. So this entire little section here, 1 over infinity, is 0. So 1 over R plus 0 inverted is just R. So it's really just the bulb in this case. Okay, so now we've got to do closed. All right, so now, when it's closed like that, we're actually not going to go through everything. We're going to notice that C is shorted, is the phrase, because now it's the opposite of this. Now C, the conductivity, or the resistance is 0. So we say 1 over R for the bulb plus 1 over 0 to the minus 1. Well, that is infinity. Okay, so we take 1 over R plus infinity is infinity, and then to the minus 1, 1 over infinity is 0. So basically, this whole thing is just taken out of the picture. It's just not there anymore. We shorted it with a wire, or really you could think of it this way. This wire just took over and made that resistor disappear. Right? So really then, this is now the same as part A of this problem. A resistor here, 2 resistors there in parallel. So you can go back and look at those old ones. In this case, this is R, this is half R. So this gets 2/3 of the EMF. And B and D both get the same voltage drop. They each get 1/3 of the EMF. So 1/3 EMF and D, 1/3 of the EMF. And the voltage drop across C is 0, because it's now just a wire. Okay, so now let's look and see which answers are correct. This is 0.6 EMF, and it goes to 0.66666 EMF. So the voltage drop across A does increase. So there you go. Voltage drop across B, does it double? No, it goes from 0.2 to 0.33333. So it didn't double, didn't make it to 0.4. Does the voltage drop across B go to 0? No. It's this one that gets shorted out, not that one. And then finally, is the voltage drop across P constant? No, nothing is constant. Everything's going to change when you throw that switch. So the answer is just A. Voltage drop across A increases.